Hello everyone, Dr. Box here again. Um, so this is lesson 11 in the series of the AQA A-level physics course, and this is the astrophysics unit. We're getting towards the end of the unit now. We've got about 2 more lessons to go after this one. And this is a sort of an overlap lesson with the one we talked about supernova before, and supernova being very useful for standard candles. But now we're going to look at the products of supernovas, which are neutron stars and black holes. Also, some of the things that you can see from Earth, like gamma ray bursts. I'm going to mention a little bit about the variation in black holes, where they appear. But importantly, there's a bit of calculation as well. We haven't done a lot of calculation for a while, so there is some calculations that are coming up there. Rather unfortunately, it's behind my head that I go there. But the Schwarzschild radius equation, which is very straightforward. There's nothing. I'm going to show you how to derive it, but you don't have to derive it for the specification. So just to be clear, I'm going to show you where it comes from, but nevertheless, you don't have to derive it. It's not a specification, and this is why I show students the specification. There are some things you have to derive, which I'll do in other lessons. Okay, so let's get cracking. So as ever, you need to recap everything that we've done so far. This is a kind of a broad idea of astrophysics. I've also thrown in some bits from other A-level bits of that. So there was calculating the radius of an atom by alpha particles and ideal gas criteria. It depends what you've done so far, but that's good to get a nuclear fission reactor. Incidentally, if you are looking at this in 2022, nuclear fission reactor does not appear in the exam this year because it's been taken out. However, if it's after that, then you do need to know about nuclear fission reactors. So there you go. Pick HR diagram. Pick the sausage diagram. Do that. Make sure you get your axes right. What's a mole? Why is it important? What's a light year? What defines absolute zero on a I don't know, pressure volume graph, if you like, and what's the definition of intensity, and how does it relate to the inverse square law? So do that. So pause the video, do 3 of those, and then get back to us. Welcome back. So title in your notes, please: gamma ray bursts, neutron stars, and black holes. We're going to be describing the origin of features of something called a gamma ray burst, which is very near to my heart. It was my master's degree qualification. I'm not going to bang on about it too much, but they are extremely interesting. The history of them is interesting as well. And then we're going to look at neutron stars, and then, of course, black holes, which is probably possibly one of the weirdest things in the universe, and now confirmed with some direct observation as well, just in this last year. And so, yeah, I'm going to recap a little bit on supernova, because obviously you can't talk about black holes and neutron stars and gamma ray bursts without talking about supernova as well. So get those in your notes. You might want to just make a note of the fact that gamma ray bursts are products of cosmological supernovae, but I'll get onto that detail. Incidentally, the picture there, the one in the centre there, is an artist's impression. Okay, that's not the picture that was taken recently. Okay, so here we go. Here's your sort of 3 rough stages of stellar evolution, the end of life of a star. So stars around the same mass of the sun and smaller, a little bit bigger, eventually become white dwarfs. Now they don't go bang. All they do is they just blow off their outer layers and they put all this gas and various bits and pieces. The physics of why they do that is not concerned in A-level, but do degree in physics in your work and you'll be told what it is. It's fascinating. And then eventually all the and you're left basically with the ash, I always call it, a little cinder at the middle, which is the white dwarfs. Very hot, very blue, very white, but nevertheless, and very dense, of course. It's something called electron degenerate, which basically means it looks like a giant piece of metal that's sitting there. And then, of course, if the white dwarf accretes material from another star, it can turn into a neutron star. But neutron stars can also be produced in the centre of stars that are roughly between 4 and 8 times the size of the sun. This does go bang. So this is a product of supernova. And then neutron stars are significantly smaller, significantly more dense, and they're essentially a giant nucleus made of neutrons, and that's why it's called a neutron star. Of course, we can't be entirely sure because we've never observed one of these directly. We've not been there, but we've seen a product of them they're called pulsars. They're very, very fast spinning objects that give out radio waves in very strong pulse. And Jocelyn Bell, of course, was credited with discovering that, even though she wasn't given the Nobel Prize. But anyway, there you go. Right, and then of course when we go to large stars, 8 times mass of the sun, that's when we become black holes. Black holes are distinctly strange. We only really see them when they're right next to other stars, destroying them effectively, which we talked about before with the type supernova 1A in the other words, the idea that something's accretion. In that case, that was a white dwarf accreting. Neutron stars can also accrete from other stars. Black holes also accrete from other stars. All of them are giving out high energy electromagnetic radiation in the form of X-rays normally. But really, the artist's impression there is what you usually associate with a black hole. And these little things coming out here, they're not visible. They're called radiolobes. Lobes are just fiery material out there where it's super fast. Anyway, there you go. So that's your three very dense objects that are coming from basically increasing in mass. Now, gamma rays come from a supernovae, which are one of the highest energy events in the universe. Now, gamma ray bursts were very, very peculiar. They were discovered because the Russians and the Americans were trying to look for gamma ray bursts coming from Earth, because that would be an indicator of a nuclear bomb test in the 1950s and 60s. But they started discovering that gamma rays were coming from space, and nobody told anything about it until a couple of scientists on each side said, "Are you detecting gamma rays from space?" And yeah, they both were. And actually, they discovered all over space, and they were coming from equally from everywhere, which tells us that they're cosmological in origin. That basically means they're outside the solar system, they're outside the galaxy. If they're in the galaxy, you'd expect a stripe across the sky of them. That doesn't happen. So gamma ray bursts are effectively the product of a very large of a supernova, and we can't see the optical part of this supernova because they are so distant, and they appear to be objects that could be like black holes coalescing or neutron stars coalescing and causing a huge explosion. They could be supernova that are so far away we can't see the galaxy that they're in. But importantly for you, they're the product of a type 2 supernovae, so they're extremely bright, and they are extremely high energy. They're equal to the total energy output of the sun over its lifetime. Never seen an exam questioning about gamma ray bursts yet, so you never know, this year might be the year. One other thing is, of course, they're extremely short-lived. They are in the essence of, they can be milliseconds, but they can be just a few seconds. And that's extremely unusual. But that also tells you that they're coming from a very small area of space. They're not elongated areas. In other words, they're coming from a distinct point, hence black holes coming together, very, very small. This is a beautiful picture of supernova 1987A. This is what it looked like from a distance, but when you get up close, you see this. Some lovely false colours on here, by the way. This is not what it looks like in space. But nevertheless, you can see it. And actually, it looks more like an hourglass. You're looking at kind of obliquely on its side, and that's what supernovas look like when they go. Fantastic piece, some energy from there. So that's a gamma ray burst. Basically, fact file, product of type 2 supernova, extremely bright, very, very far off, product of a type 2 supernova, almost certainly, or some black hole and neutron stars. Coalescing is the word, coming together. Right, so what's a neutron star? So neutron stars, again, produced at the centre of type 1A and type 2 supernova. Type 1A, of course, is neutron stars produced from a white dwarf, whereas type 2 supernova is just a single star. They're greater than 1.5 solar masses. They're made of neutrons. Strong pulsing radio sources as well. So the pulsar lighthouse effect. The reason we see these pulses of radio waves is basically the pole of the spinning neutron star. So the radio pole, the radio lobe, the firing out of radio waves comes into our direction across the Earth every now and then. It does it in a millisecond. A day is a millisecond. Neutron stars are significantly smaller than the Earth. You can see here. They're about 12 kilometers in diameter. So think of something that's about, 8-9 miles away from you, or 12 kilometers. That's the full diameter of a neutron star. But yet they've got the mass of the Earth and more into that density. They're spinning very quickly, like I said, 1 millisecond. And the Crab Nebula is an example. So there's a pulsar right in the middle of the Crab Nebula as well. So there you go. And this is kind of guesswork, really. Nobody really has done an experiment to chop a neutron star in half. We know its mass. We know it's probably got solid crust. There's something heavy liquid, mostly neutrons, with other particles. There's a lot of research on this, but let's face it, you can't slice a neutron star in half or do any sort of seismic tests on it. So basically, it's like a nucleus. It's extremely dense. And to even denser objects, the densest object in the universe, black hole. And it's not black and it's not a hole, really. It's a good name, but you've got to think of it as a super, super dense object where space-time itself has been folded in itself. The reason why it's black, of course, is that light can't escape. That's why we call it black. And it's a hole, basically, because it seems like everything that goes down disappears forever, which is pretty weird. I've done the derivation here. Basically, KE lost equals GPE gained. Depending on what you've done beforehand, this is, of course, KE half mv squared. This here is your potential energy and the distance r away from the centre of mass. And if you equate those, you rearrange, you cancel things out, and then the key part. The escape velocity of a black hole is the speed of light. So that is the speed of light. You have to, that is the definition. And that happens at something called the event horizon, and that happens at a distance away from the center, which is called the Schwarzschild radius. So those things, the escape velocity will exceed the speed of light at the event horizon, which is at the Schwarzschild radius, which can be calculated using this equation here. This is the Schwarzschild radius, 2 times universal gravitational constant, mass of the black hole, and the speed of light squared. So not a particularly difficult equation to handle, because the only variable really here is mass, because of course everything else is constant on here. So you can see it there. Supermassive. This sounds like some sort of teenager gone wrong and trying to get a word that's like huge, but even more massive than massive. But no, supermassive does mean millions of solar masses. And these can go from small black holes, stellar black holes, right up to the supermassive black holes, which exist in the center of every galaxy, we believe. Everyone we've looked at appears to have the evidence of a supermassive black hole. And it all started with 3C273, which was an object that looked like a star, but wasn't a star. And that's why it was nicknamed a quasi-stellar object, and that's where we get onto this object called a quasar, which is almost certainly a supermassive black hole, which looks like the picture that you can see there. And this has a supermassive black hole at the center of it, a supermassive black hole. And this has got a huge number of entire stars being consumed in the center, very high output, and it's long way off, high redshift, very large distances, very early period of the universe. And they are very strong X-ray sources as well, because obviously things falling into it get very hot. So calculation from here, Schwarzschild radius is what you need to know for the A level. Your escape velocity greater than speed of light, event horizon, Schwarzschild radius, exactly the same thing. Just to put it into context, I talked about space-time earlier. Space-time is effectively the fabric in which everything is put into and everything moves forward in time. So you can imagine putting a sun, you've probably seen lots of these on the internet. People put a bowling ball in the middle of a trampoline and it goes down. It's a perfect model for how gravitating objects bend space-time. And it was what Einstein developed in the early 20th century and fits perfectly. It explains and predicts all that we've seen about the universe in terms of time dilation and length contraction. If you want to know what those are, go and do a degree in physics. It's brilliant. As you can see here on the black hole, you've got the event horizon down here. So this is what you'd be calculating during the A-level qualification. And if you want a little bit of beauty, this is a picture from the Wildfield planetary camera on the HST, the Hubble Space Telescope. And you can see these little squiggles here. This is pictures of background galaxies that are behind this central object here, which is a huge elliptical galaxy called Abell 2218. And these are galaxies that are sitting behind it, but the light has been bent around it, because the light, as it comes near this, bends around here and comes through here. And it's called gravitational lensing. And it's a way in which we can see way deep into the universe. And it's being used for lots of different techniques for it being able to look at all types of galaxies. And what was weird about this is, of course, the spectrum of this star, this galaxy here, was exactly the same as the spectrum of this, and this, and this. And it was the same galaxy. It was just multiple images that had been lensed around it. And that's how we worked out that it was lensing. Brilliant piece of astrophysics. So let's get on to exam questions. Here we are. Centaurus A is an example of an active galactic nucleus. That's another byword for this black hole that's at the center of a supermassive black hole. So it's where all stuff, another byword for that. So active galactic nucleus basically means there's a black hole and there's stuff falling in over a very small area. Many astronomers believe there's a supermassive black hole at the center of such galaxies, producing a quasi-stellar object, very large distance, looks like a star, that's why it's called quasi-stellar, as it consumes the material of its nearby stars, just like it says before, all coming in. Explain what is meant by the event horizon black hole. Just say it is when the escape velocity is greater than the speed of light. The radius at which the speed of light. Mention Schwarzschild radius in there as well. Remember, event horizon is not a general, don't think go to describe what a black hole is. It's just the escape velocity exceeds the speed of light. So, mass of a black hole is 60 million times the mass of the sun, calculated the radius event horizon, straightforward stuff. The hard bit about this is, of course, the mass of the sun is buried on your formula sheet, so you have to go and look for it, and that's what panics a lot of students. I've given it to you on the top right-hand corner here, just to save you time. So 1.99 times 10 to the power of 30 kilograms, and then, of course, 2 marks for that. Get your equation down, get your numbers in, make sure you've got your powers in the right place. And then it said, calculate the average density of matter within its event horizon. Great question. So this basically means that you have to calculate the volume of the sphere with its radius as the Schwarzschild radius. And then, of course, in that, you put that amount of mass. And you end up with a number that's quite surprising, actually, that's not totally dissimilar to the density of normal stuff like metals and things. So you'd be expecting a really, really high number, but actually it doesn't work out that much. So there you go, really good one. Go away, get your calculator out, do those calculations with my tips, and come up with the numbers. And I'll show you the answers in 3, 2, 1. And there they are. Okay, there you go. Boundary where escape velocity is equal to c. And there you go. That's Schwarzschild radius. Sticking your numbers. This is gravitational constant. There's your 60 million. And yeah, incidentally, look out for those words, the million there, because sometimes students can just put 60 in and forget that it says million after it. And there's the speed light squared, so 10 to 11, typical kind of Schwarzschild radius. And then density equals mass divided by volume. I love density because mass divided by volume. 60 million, and then there you go, there's the radius. There's radius in there of the volume. And you end up with that, look, 5,000 kgs. It's about density of metal, quite surprising. Okay, so there's a roundup. We've did the definition of supernova before in another lesson. Gamma ray burst, we've done that. We've done this one. Type 2A supernova, that was previous lesson. Again, supermassive blow of the center of galaxies, we've done that, and then we've done calculation of event horizon of black hole. And also I've given you a little bit about the idea of neutron stars and bits and pieces as well. Because it says neutron stars up here, the only mention of neutron stars is down here. I've given you the fact file anyway, just in case you need to know about stars. It's not mentioned in the specification, but I worry about when things are mentioned here and here that they're quite keen on them. Okay, right, I'll see you next lesson.